the Poisson universal enveloping algebra and the Poisson differential operators of a generalized Weyl Poisson algebra. So the main subject of my talk are Poisson algebras, and they are called generalized Weyl Poisson algebras because as associative algebras, they are generalized Weyl algebras, but commutative. And to this class of Poisson algebras, one can attach so-called the Poisson universal enveloping algebra in the same, sort of in the same way as for any Lie algebra, one can produce associative algebra, which is called the universal enveloping algebra, and the representation of the Lie algebra is the same as representation of the associative algebra, which is universal enveloping algebra. It's universal enveloping algebra. The same story for Poisson, for any Poisson algebra. There is its so-called Poisson universal enveloping algebra, but this construction is given. The existence of this algebra for every Poisson algebra is given as a universal object in certain categories. So it means it's a piece of work to find generators and defining relations. So the goal of my talk is simply introduce the object, then we will find the Poisson simplicity criteria for these algebras. So we will describe its Poisson center, look at some ideals, look at the regularity criteria for these algebras, and also consider the generators and defining relations of the Poisson algebra for this class of Poisson algebras, and give a simplicity criteria for these algebras. And it turns out when this algebra is simple, this is precisely the so-called Poisson algebra of Poisson differential operators. So it's kind of, you can study it using the modules. Okay, so we start with the arbitrary field, and Poisson algebra is commutative associative algebra, which is also a Lie algebra, and this is a bracket. And two structured associative and Lie are related via so-called the Leibniz rule. And let me introduce some concepts. I will need them in order to introduce this object. So for algebra D, we denote by the KD is the set of all K derivations. And if addition, the algebra D is also a Poisson algebra, then we denote P there is the set of all Poisson derivations, i.e. the derivations of Poisson algebra. So by definition, it consists of a derivation of associative algebra that also a derivation of the Lie algebra. And the set of derivations of arbitrary commutative algebra is a Lie algebra with respect to the commutator of functions. And the set of Poisson derivation is a Lie subalgebra. Now for each, and for each, so we have plenty of Poisson derivations, so-called the inner derivations or Hamiltonian vector fields, which are denoted in this fashion. So for each element A of D, we have a Poisson derivation, which is given by this rule. Simply the bracket of A, and this is a variable. Okay, so hence we have a map of Lie algebras from Lie algebra D to the Lie algebra of inner derivations given by this rule. Hence there is a kernel, and kernel is the ideal of this Lie algebra, and this is by definition the Poisson center. Right, so now let me recall the definition of class of associative algebras, which are called generalized Weyl algebras. So these algebras are non-commutative, but we will need commutative version. Okay, so we start with arbitrary ring D. We look at the n-tuple of commuting automorphisms and the n-tuple of elements of the center of this algebra D such that satisfy this condition. Then the generalized Weyl algebra, which is denoted in this way. This is algebra generated by the ring D and two n elements. So n-tuple of x's and n-tuple of y's. and subject to these defining relations. So when letter y and xi meet, they produce element, the central element, central of this small coefficient ring. And when they meet in the opposite order, they produce the element twisted by the automorphism. And we have a skew relations, like for skew polynomial rings. And letter of these different indices, they commute. Okay, so nth Weyl algebra, which is by definition supposed to have a ring or field, then this is algebra generated by 2n elements, x's and y's, subject to the classical commutation relations, where delta ij is the canonical delta function. So this algebra has another description as the algebra of polynomial differential operators. So these are polynomials, and these are partial derivatives. So then this algebra can be represented as a generalized Weyl algebra. Hence, we have to look at this coefficient ring. So this is a polynomial ring in n variables. So we have to choose commuting automorphism. So these are the simplest possible automorphism, simply shifts in letters in different direction by 1. And the elements simply h1, hn. And the map from the Weyl algebra to this algebra, which is given in this fashion, is an isomorphism of algebras. Okay, so now we come to generalized Weyl Poisson algebras. Right, so this is Poisson version of associative generalized Weyl algebras, if you want. Of course, I don't have time to look at the kind of motivation, but you will see. So we start with arbitrary Poisson algebra. In the previous constructed, we started with arbitrary associative algebra, but here is a Poisson algebra. In previous construction, we started with commuting automorphism. Here we start with a commuting Poisson derivations, n tuple. And the n tuple of elements of the Poisson center, such that this condition holds. Then the commutative generalized Weyl algebra. So Poisson algebra by definition is a commutative algebra, hence all these automorphisms are the identity maps. So in this situation, this algebra is a factor algebra of the polynomial algebra is 2n variables with coefficient from d via these relations. And this algebra admits a Poisson structure, which is given by this rule, right? So when we look at the y commutator yi and d is an element of d, we have this element. And when we replace by x, we have minus here and xi, and commutator on yi and xi, this element. And the different letters with different indices, they commute. Okay, so we don't know this algebra, generalized Weyl Poisson algebra. So this is a Poisson algebra, which is also generalized Weyl algebra. So we replace this bracket by Kelly bracket in the definition of generalized Weyl algebra. Okay, so this algebra is a Zn graded Poisson algebra. So it means algebra is direct sum of A alpha belongs to Zn, and this is a free module over D. And this is a particular element, these are explicit elements, right? Roughly speaking, product of x's and y's in the obvious way. And graded Poisson algebra means that this is a graded associative algebra and graded Poisson algebra. So two grading structures as associative algebra and Poisson algebra. So now I'm going to explain the simplicity criteria, Poisson simplicity criteria. So when we have a Poisson algebra and we have an ideal of an associative algebra A, and this ideal is called a Poisson ideal if this inclusion holds. It's clear that 0 and algebra A are Poisson ideals, but if these ideals are the only Poisson ideals, the algebra is called simple Poisson algebra. Okay, so we deal with n tuple of Poisson derivatives of this Poisson algebra A, and suppose we have an ideal of this ring D, and this ideal is called D invariant if this ideal is D di invariant for derivatives. And by this, we denote this set of all d constants. So it means the intersection of kernels of all derivations. And this is a subalgebra, and it is called the ring of d constant. So the next theorem is a simplicity criteria for Poisson, for the generalized Weyl Poisson algebra. So we start with arbitrary generalized Weyl Poisson algebra, right? That this algebra is Poisson simple or simple Poisson algebra, if and only if three condition holds. The original Poisson algebra has no proper d invariant Poisson ideals, and this condition holds for these defined elements. So the ideal generated by element ai and di ai is equal to the whole algebra, and the Poisson algebra is simple. And the Poisson center is a field. And the next proposition gives, what does it mean? Gives a necessary and sufficient condition for this subalgebra be a field. So we have an arbitrary generalized Weyl Poisson algebra. Then the Poisson center is a field if and only if characteristic is 0. The D invariance of the Poisson center is a field, and certain explicit subspaces are equal to 0. Subspaces are indexed by alpha from Zn, which is non-zero. And these spaces are given in this fashion. So what does it mean? So this is an element of d constant, such as the inner derivative, which is determined by this element, is equal to the, roughly speaking, the sum of these derivations of the Poisson algebra with this condition. Okay, if you ask questions, suppose we drop this condition, 3, right? Suppose the algebra does not satisfy this condition, but satisfy this two. So what we can say about the ideals? And the theorem is that in that case, any Poisson ideal, suppose condition 2 and 1 hold, but suppose condition 3 doesn't hold, that every Poisson ideal is intersect the center. So it's kind of, let me look at some examples. So suppose we have a commutative algebra with trivial Poisson bracket, right? So it means the bracket is 0. Then the Poisson center is simply ZD. So these elements can be chosen from the ring. And the Poisson derivatives are equal simply the derivatives of the algebra. So simply this tuple are commuting derivatives of this algebra with this condition. Then we can produce Poisson algebra. And in particular case with n equal 1, then there is no restrictions. So there is no such a condition. So it means in this situation, we can choose element of a ring and its derivative in arbitrary fashion. Okay, so the most important Poisson algebra is this one. So we have a polynomial ring in 2n variables, and the Poisson structure is given in this fashion. So this is sort of like a Weyl algebra in a Poisson fashion, right? And this is also generalized Weyl Poisson algebra in a similar way as a Weyl algebra is a generalized Weyl algebra. So we will have to choose this ring D, which is a polynomial ring in n variables. Then we will have to choose n tuple of elements of this ring. This is the same as for the Weyl algebra. And we have to choose the derivative of this ring. And this is a partial derivative. So the map is natural. But of course, in this construction, we can replace this polynomial by any polynomial in H1, and similar story, this polynomial in any polynomial in H1. And here we can multiply by any polynomial in HI. And conditions for the existence of generalized Weyl Poisson algebra are satisfied, since we have this large class of algebras. So we start with arbitrary n tuple of polynomials, and arbitrary derivatives of these polynomials, also arbitrary. And then we can produce the generalized Weyl Poisson algebra. For example, for the particular choices of A and D, we have the algebra above. So now, when we look at so this is a large class of algebras, and many classical Poisson algebras belongs to this class. So let me demonstrate this by example of USL2. So USL2 is associative algebra, but it has canonical structure. It has canonical filtration, such as associative graded algebra is a polynomial ring in 3 variables, and it has canonical Poisson structure. And this Poisson structure is an example of this algebra, which I'm going to explain, which is much more general class. So we start with a polynomial ring in 2 variables. So morally, this is kind of rudiments of a Casimir, taking associated graded image of it. And this is a Cartan element, right? So now we have a generalized Weyl Poisson algebra of degree 1. So there is no restriction on element A and D. We take arbitrary element and arbitrary derivative. And we have this Poisson algebra. In particular case of USL2, so we have SL2, right? So we have USL2. We have the canonical filtration by the total degree of these variables. Take the associated graded algebra. This is a polynomial ring in 3 variables, x, y, and z, h. And it has a canonical structure. Poisson structure simply replace this bracket with the Kelly brackets. And then the image of the Casimir, which is this one, which is quadratic, because of course Casimir in SL2 has a linear terms, but when we take its graded image, linear terms disappear. And using this Casimir, you can write down this Poisson algebra as a generalized Weyl Poisson algebra in this fashion. So element A is this, and the derivative is simply partial derivative. Right. Okay, so and also many other algebras can be represented in this fashion, like. And when we look at the tensor product of these algebras, it's also a Poisson algebra in the obvious way, so I will not give the detail. So now look at so we have an associative algebra and this set of derivations. So we denote in this way the ring of D constants, which is simply the elements that are killed by D. And the ideal is called D invariant if this inclusion holds for all derivatives. So now we look at the Poisson center. So we start with arbitrary generalized Weyl Poisson algebra, and then the Poisson center is a Z graded subalgebra, where these pieces are given explicitly. So each piece is simply D alpha, which was introduced at the beginning of the talk, right? This is precisely this definition. Okay, so in general, this Poisson center is small. Suppose we have a characteristic 0, the same algebra, arbitrary algebra as above, but suppose field is characteristic 0, and this element a non-zero divisor. For example, if D is a domain and this element is not 0, these conditions are satisfied, that the Poisson center collapses to the D constants of the Poisson center of this coefficient ring. Right, so unfortunately my time is up, so I simply skip. So there is an explicit description of the minimal prime for arbitrary commutative generalized Weyl algebra. So this is explicit description. Also description of the prime ideal and the factor algebra's ideal over the minimal prime. It's also a generalized Weyl algebra. It's possible to find its quotient algebra and to compute the transcendence degrees. Transcendence degrees, we need it coincides with a crude dimension, and hence when we have the regularity criteria, this will be precisely the global dimension of the regular algebra. And there are 2 regularity criteria. Unfortunately, all this homological algebra is very technical, so I simply give you idea because I want to go to universal enveloping Poisson universal enveloping algebra. So this is the second regularity criteria. So we started with arbitrary commutative generalized Phi algebra, such that the coefficient ring is a commutative algebra of a center over itself is a Poisson module, where this delta A is simply the Hamiltonian vector field corresponding to A. Okay, so now we come to the main object, very recent object, I don't know, maybe during the last 20 years or so appeared, that for any Poisson algebra, there is its so-called associative algebra, which is called Poisson universal enveloping algebra, which is given by the property that, no, this is on level of intuition because it's also technical, that every Poisson P module, so this is a module of a non-associative algebra, is a module of an associative algebra and vice versa. So the same story as for Lie algebras and its universal enveloping algebra. But the difference is, since this algebra existence is given via universal property in certain category, this is in strike contrast with the universal enveloping algebra, which basically have the same relation as a Lie algebra, which is given in a very explicit way. So the point is how to describe this algebra as associative algebra, i.e. via generators and defining relations. And I'm going to explain for this particular class of Poisson algebras, which are generalized via Poisson algebras. But first, let me introduce very important concept, so-called Poisson differential operators. So we start with arbitrary Poisson algebra. Then this is a commutative algebra, hence we have the rings of differential operators. So algebra is not smooth. So this is a nasty object, usually not Noetherian, not finitely generated, not anything. And hence we have these nice derivatives, so-called inner Poisson derivatives or Hamiltonian vector fields. And we look inside this algebra, we look at the algebra which is generated by algebra of functions and these derivations. And by definition, this algebra is called a Poisson differential operators of the Poisson algebra P. So now next theorem is simply for arbitrary Poisson algebra D. Arbitrary algebra can be represented in this way. Take the polynomial ring in arbitrary variables, localize it and factorize it, right? So this is the most general construction of any ring. And when we look such a ring, which is also Poisson algebra, and look at the generalized Weyl Poisson algebra and take its universal enveloping algebra, that this algebra is generated by the algebra A itself and these elements, and subject to three types of relations like that. There is a logic behind of them, but in order to explain intuition, it takes time. But the moral is, it's a much more complicated object than universal enveloping algebra. It's a mixture kind of many things. And that is why it's difficult to even produce one module, Poisson module, because it has to satisfy many conditions. For example, right, so unfortunately I have to skip this. I wanted to explain why it's difficult for USL2, this kind of associative algebra, to classify simple module, because it will not be like a block classification. If we immediately have much more larger objects, like roughly speaking, in block we have Gelfand-Kilo dimension 2, but here we have like Gelfand-Kilo dimension 4 with this relation, so it's kind of completely different kettle of fish, and it will not be easy. So now simplicity criteria. So here we assume characteristic 0, and we take the arbitrary generalized Weyl Poisson algebra in the following sense. We start with this is the essentially arbitrary algebra, essentially finite type. So we have polynomial ring, factor by ideal, localize it, and we assume this ideal is prime, hence this algebra is a domain. And these are generators of this ideal. Hence we have the Jacobian matrix, simply partial derivatives of the generators of the ideal. Since this algebra is Poisson A, hence we have this matrix of all, and these are the sort of generators of this algebra. Of course, this is a localization, cannot be generated, but since kind of Poisson structure commute with localization, kind of the Poisson structure is given by this matrix. And we denote the D by rank of this matrix. Rank means over the field of fraction of this domain. Then we have a general criteria. So we have this generalized Weyl algebra, arbitrary generalized Weyl algebra, this coefficient in this algebra, where D and R as before. Then the universal enveloping algebra is simple. So the following conditions are equivalent. This algebra, the Poisson universal algebra, is simple if and only if the algebra of Poisson differential operators is simple and there is relation between four numbers. So we have number n here, capital N, and these two ranks. And also there are finitely many explicit elements of the rings that equal to 0. They are given by certain differential operators act on explicit elements, and everything is explicit, but it's a very sort of technical to explain it. And the third equivalent condition, then Poisson algebra is simple. So we know the criteria. So criteria is rather very easy, right? And this relation between these four numbers, and the same story, the same finite number of elements which are given explicitly are equal to 0. So very easy to check. So it means if you want to check simplicity criteria of these rather ugly objects, or this rather, you see, object, which is also not easy to handle. And here we have a nice criteria, Poisson criteria, and kind of this condition are just also easy to check. So, and moreover, and this is the last slide, nice timing, it's 1950. So then this, if the above condition holds, that actually the Poisson universal enveloping algebra is in fact the algebra of Poisson differential operators. And this algebra, and hence using this isomorphism, it's easy to show that this algebra is Noetherian domain, which is not obvious. Usually it's not domain even if you start with a domain. This algebra is not a domain. And moreover, the Gelfand-Kirillov dimension of this algebra, and of course coincide with this algebra because they're isomorphic, and this is a double of the Gelfand-Kirillov dimension of the algebra A, generalized Weyl algebra, this commutative, which is also to this number. So this number basically is the Gelfand-Kirillov dimension, this algebra. Okay, thank you very much for your attention.
Thank you, Volodymyr, for an interesting talk. And are there any questions?